All right, pre-calc, here we go. Another day learning some things about polars, this new way to plot points. We're going to extend that today and actually look at graphing polar equations. So things to know about polar equations. No longer will we be writing equations in terms of x and y, but we'll be writing them in terms of r and theta. We will, in subsequent lessons, be looking at how to convert back and forth between rectangular and polar equations. So there will be a connection between them. But today we're going to look at how do we just deal with these r's and thetas graphically. So some examples of what some polar equations might look like. They will all have r's and thetas or some combination thereof. Sometimes you'll just have an r, meaning that distance from that pole will always be 5. R equals 5. Or maybe R would equal 3.5 sine of theta. That would be an example of a polar equation. You can have also something like -6 cosecant of theta. So those reciprocal functions will also come into play. Or you might just have something with theta. Theta equals pi. So our job will be to explore different types of equations and see their resulting graphs, see if we can make some generalizations about their characteristics. And that's what we'll be doing over the next couple of lessons. We're going to just look at some simple graphs here. What if we just have r equals 2? Now remember, r is that distance from the origin, that directed distance from the origin. And so I think of r as that radius. It's always 2. So we are always a distance of 2 from the pole. And we always begin with theta at 0. It just, not always, but it is in most cases where we begin. So here we're at a distance of 2, and then if we go pi over 6, we're a distance of 2 away, and at pi over 3, we're a distance of 2 away and 2 away. And you notice, if we're always a distance of 2 away as we walk around those angles, no matter what the angle is, 2 away, we actually form a circle. Circle with radius 2, that is what the equation of r equals 2 is. And that makes sense. Radius of 2. No matter what the angle is, we are 2 units away from the pole. So if our radius is negative, that tells us that we would go backwards. Normally, if it were r equal 4.5, we would go 4.5 at an angle of 0 radians, but we're going backwards 4.5. So it actually is like it's starting off right here. That would be our first point. And normally we would travel around counterclockwise the unit circle, but going the opposite direction because the r is negative. It would be traveling from 0 to 2 pi would be traveling around this way. And so we still get a circle with radius 4.5, just like we would if the equation were r equals 4.5. But if we watch it plot point by point and grow this graph, it actually begins over here at pi and works its way around. We can also have theta be a constant. So in these first two, r was a constant, the distance away from the pole was constant, and the angle could change. When you have theta equal to something, the angle will stay constant, but the distance away from the pole will change. So pi over 3, we will consistently be at an angle of rotation, pi over 3, but our distance will change. So we could be any of these distances all the way out to infinity there. But it's not just array, because we could have r be negative, and so it actually could go back this direction as well. And so when you have theta equal to an angle measure, you get a line. Same thing, number 4. theta equals negative 7 pi over 6. That happens to be coterminal with 5 pi over 6. And r could be anything. Whoops, I'm not drawing that very straight. So it would be that line right there. I should have brought a straight edge out. Hope yours looks better than mine. Theta equals a constant. We have a line. R equals a constant. We have a circle centered at the origin, or that pole. But equations get a little bit more complex than that, and so we want to up the ante just a little bit. What if we throw a trig function in there? R equals 2 sine theta. We're going to begin to explore this by just plugging in some values between 0 and 2 pi, like one trip around the unit circle. What kind of graph would that form? So I'm going to think of this as my unit circle and sort of visualize my ordered pairs. You could grab your unit circle if you wanted to. We're just going to plug in different values of theta and see what comes out as r. So if theta is 0, sine of 0 is 0, 2 times 0 is 0. Moving to pi over 6, the sine of pi over 6 is 1/2. 1/2 times 2 is 1. We're skipping these ones. You wouldn't have to. You could put them in there if you wanted to, the pi over 4s, but the table here doesn't have it. Let's go to pi over 3. Sine of pi over 3 is root 3 over 2. Root 3 over 2 times 2, the 2's cancel out, and we're left with root 3. 1/2, sine of 1/2, pi over 2. Sine of pi over 2 is 1 times 2 is 2. And then we begin to go back down. That was the maximum sine value. And so we're going to see some symmetry in our graph here. Sine of 2 pi over 3 is root 3 over 2 times 2 is root 3. 5 pi over 6, sine is 1/2 times 2 is 1. You can see that we came up to a maximum, went back down. At pi, the sine is 0. So 2 sine of pi is also 0. Then we're going to head into the negative sine values. So sine of 7 pi over 6 is negative 1/2 times 2 is negative 1. 4 pi over 3, that's negative root 3 over 2 times 2 is negative root 3. You can see some symmetry even here, can't you? And then the sine of 3 pi over 2 is negative 1 times 2 is negative 2. 5 pi over 3, negative root 3 over 2 times 2 is negative root 3. And then 11 pi over 6, sine of that is negative 1/2 times 2 is negative 1. And then at 2 pi, we would be back to 0 if we want to extend that. So let's plot these points now and see what this graph looks like. I have, remember, it's our ordered pairs are going to be r comma theta. And so we've got 0, 0 here. Then at pi over 6, we're a distance of 1. And at pi over 3, we're a distance of root 3. Now, things to keep in mind here, root 3 is approximately 1.73. So almost 1 3/4. So 1 3/4, almost that. That's 1 1/2. Oh, not, yep, almost 1 3/4. There we go. Then we've got pi over 2 is 2. And then root 3 again. And 5 pi over 6 is 1. And back to 0. And now at 7 pi over 6, we are at negative 1. So I'm at 7 pi over 6, but I'm going to go backwards 1. Notice that plots the point exactly on that pi over 6, 1 point. And then at 4 pi over 3, I'd be going back root 3. Well, that plots right there. And this point at the 3 pi over 2, negative 2, I'd be going back 2. And so I actually, between 0 and pi, take this path. And then from pi to 2 pi, I repeat that path. And so it has some repetition in there. This should be a little bit wider. All right, so that is 2 sine theta. It actually is a circle that extends up to on that vertical axis. Let's try a couple more. All right, I'm going to make a nice little table here for the cosine, although actually I'm not sure we need the table. We can walk around the unit circle. Because at 0, what is the cosine of 0? Maybe cosine of 0 is 1. So I'm at that point right there. At pi over 6, cosine pi over 6 is root 3 over 2. That is 0.866. That's about right there. Cosine of pi over 3 is 1/2. So that's going to be right here. Maybe I'll do pi over 4 as well. Pi over 4 in there is root 2 over 2. Root 2 over 2 is about 0.707. You know what? I plotted that point wrong, didn't I? I thought that looked kind of funny. 0.866. You have to follow your scaling. And 0.707. And then cosine of pi over 2 is 0. Cosine of 2 pi over 3 is negative 1/2. So at 2 pi over 3, I'm going to go negative 1/2. And at 3 pi over 4, that would be negative root 2 over 2. So I'm going backwards 0.707. And at 5 pi over 6, the cosine's negative root 3 over 2, negative 0.866. And the cosine at pi is negative 1, so I'm going to go backwards 1. And you'll notice here that I begin to repeat then again. So we go around. It only takes one time to go around one time, only from 0 to pi. And so then from pi to 2 pi would be the second time around with those negative values. All right, so aside from my little mix up there, sorry about that. Look at what we have here just by some patterns, and we'll see if we can work with those. With the 2 sine theta, notice we have a circle that was up on the vertical axis. Isn't the sine is y? And look at that, the sine function gives us something that's centered on that y-axis. And look at the diameter. It has a diameter of 2, and there was a 2 in front of there. Look at the cosine. R equals cosine theta. That is a circle of diameter 1, and it is symmetric on that x-axis, because cosine's x. And so we can actually use that to help us graph these a little bit. If we look at number 7, we've got a sine function. Sine is y. So we're going to have a circle That is coming on the y-axis, but it's -3. So instead of being up here, it's going to stretch down to -3. So we're going to have a circle of diameter 3 here. It's going to be on this portion. And if we begin to plot some points, let's see, at sine of 0 is 0. So it's going to start here. And sine of pi over 6 is 1/2. And so that would be -3/2. So -3, 1, 2, -3/2 is right there. And at pi over 3, √3/2. And I'm just going to throw some things in my calculator. And you could put them in and let the calculator do those sine functions as well if you want. But I'm looking at -3 times √3 divided by 2. So I'm looking at -2.6 really. So I'm going to come back here to, let's see, 2.6 would be about right here. And then I know at 3 pi over, that's actually pi over 2, sine of pi over 2 is 1 times -3 is -3. At 2 pi over 3, the sine is √3/2 times -3. I already have that value, so it would be over here. And at 5 pi over 6, that's the 1/2. Sine of 5 pi over 6 is 1/2 times -3 is -3/2. So instead of going 3/2 this direction, I'm going 3/2 this direction. And so 1, 2, 3/2. And then sine of pi is 0. I'm back here. And again, that pi to 2 pi is going to just repeat this graph right here. If it feels strange, that's because it is. It's a whole new ball game here. Okay. Number 8, we're looking at for cosine of theta. That's the cosine of theta. So I should see a circle coming around and being split by that x-axis because cosine's x. And so I'd be coming out here 4, and I'm going to have a circle somewhat here. And I could walk through those points and find my exact points at these angle measurements, but it will in fact go out to 4. And in your homework, you don't have too many. I would like to see those exact points. Let's look at number 9. There's a cosecant there. That's kind of scary, isn't it? But remember, cosecant just means the reciprocal. So let's think about reciprocals. This really is 1 over the sine of theta. So the sine at 0 is 0, and the reciprocal of 0 is undefined. So let's go to pi over 6. All right, so at pi over 6, the sine of pi over 6 is 1/2. The reciprocal of that is 2. So I'm a distance of 2. Let's do pi over, we can do pi over 4. Sine of pi over 4 is √2/2, so the reciprocal of that is 2 divided by √2, which is 1.41. So 1.41, something like that. About right there. At pi over 3, the sine of pi over 3 is √3/2, so 2 divided by 3. I'm just putting these in my calculator, you can see. I'll scoochie that over so we can see that. 1.51. So, I'm sorry, 1.5. So something like that. And let's do pi over 2. Sine of pi over 2 is 1. The reciprocal of 1 is, in fact, 1. Are you noticing something about these points? Well, let's keep going and we'll see what happens. 2 pi over 3, that's going to be the same value as pi over 3, right? It's going to be right there. 5 pi over 6 will be out at 2. Notice these are all forming a line. They are, in fact, linear at a height of 1, right where that pi over 2 is. And it is, in fact, a horizontal line crossing that y-axis. Okay. Looking at number 10, you make some predictions about number 10. It's not the cosecant function. It is the secant function. And so let's put in some values and see what happens. This is like 1/2 times 1 over the cosine. Well, the cosine at 0 is 1, but we want half of that. So it will be at 1/2 comma 0. At pi over 6, the cosine is √3 over 2. So the reciprocal of that would be 2 divided by √3. I already have that on my screen, times 1/2. And I get 0.577. So that would be 0.57, somewhere about right there. At pi over 3, the cosine of pi over 3 is 1/2. 1/2, the reciprocal of 1/2 is 2. And 1/2 times 2 is 1. So we have that right there. Do you see what's happening? I actually have a vertical line. If you kept it going, it would be vertical. So secant of theta is going to give us a vertical line. Look where it crosses that axis at 1/2, and we happen to have a 1/2 there. Here, the cosecant is a horizontal line, and it crosses that axis right there at 1, the coefficient. Not written, but it is in fact 1. And so here at 11, we've got a cosecant of theta. Well, that's going to be of that horizontal form. Where's it going to cross? It's going to cross at -2. So I can come down here at -2, because going the opposite direction of that negative. And I'm going to have a horizontal line. So we're going to begin to make some connections as to what the graphs will look like based off of the equations. Now, the beautiful thing is that you can actually graph these on your calculator and check. Okay, let's take a look here. I've already changed my calculator because I was practicing, but we're in polar form. So instead of the function mode, which is our y equals, you need to actually go and choose polar. And you can play with this. We're not going to go through all of this, but when you go into the y equals button, it now is r equals. So if I want to look at r equals cosine of theta, well, how do you get theta? Well, because I changed the mode on my calculator, this mode here, it has switched from this button being X to this button being theta. So if I press that, I actually just get my theta. And we could do a standard window. Let's see what happens there. Look at that. It's pretty tiny, but we do in fact get that graph. We can, look at this. Theta goes from 0 to 360. I'm in the wrong mode. I'm in degrees because I was doing some things in degrees with our lesson before. So I'm going to change to radians, and I'm going to do a standard, and I'm going to see if, yep, it changed to radians. And I can change the X min and X max to look like here. I'm going from -3 to 3. Maybe I'll go -5 to 5 in each direction so you can see. There it is. And it looks a little more egg-like than circle-like here, and that's because I've got a rectangular screen. You can actually change this to square up your window, and then you'll get a better picture. You can see that is, in fact, a circle. Now, if I go to check this second equation here, it was -3 sine of theta. Watch where the graph begins. Remember how we were plotting and we said that since it was negative, it was going to begin in the opposite direction? See how it did that as well? It graphed with those negatives. So you can go through and check your graphs and play with it. It's a little bit different and new, and I think you'll enjoy that. Your homework for tonight is to finish that homework number 1. That second page, and you can just submit the second page. If you didn't submit the first page yet, submit them both, but work through some of those graphing pieces. Do email me with any questions. This is some newfangled stuff that we have, and so it's going to take some time to process. So let me know. I'd love to help. Talk to you next time.